Welcome to the deep dive. This is where we take a whole stack of sources and just, pull out the key insights on really complex topics. And today we're going back to Britannia, the amazing, huge world of Ultima Online. For so many of us, back in the late 90s, that was what an online world could be. You remember it, right? Those rolling hills, the deep dungeons, this feeling that it just went on forever. As you were wandering around back then, maybe you thought, like I did, how on earth did they do that? How did the UO team create that terrain? It looked so, well, real, especially for 1997 with the tech they had. So, our mission today, unpack that exact question, and I think we'll find some really fascinating, timeless ideas for game development now, maybe even if you're looking at doing something similar, say in an engine like Monogame.
And the sources we have for this, they're frankly incredible. We're not just guessing here. We've got insights from Zaindupia, who's this amateur dev, who literally reverse engineered the UO client, built his own. Just an amazing passion project. But, maybe even more astonishingly, we have direct input from Raf Koster, the original lead designer of Ultima Online, himself.
Wow.
Yeah. So you, listening right now, you're about to get a real insider's perspective on how this legendary game engine actually worked. It's like getting a backstage pass to, I don't know, a really pivotal moment in game dev history.
Okay, this is going to be good. Let's start unpacking this because it really was a puzzle. I remember playing back then, and you're in this 2D isometric world, right? Classic view. But unlike a lot of games from that time, UO's ground wasn't just flat tiles. You'd see these little hills, gentle slopes, dips, actual rises in the land. And the amazing part was your character actually looked like they were moving up and down
Yeah.
on the z-axis. As you walked over this rippling ground, it just felt so much more dynamic, alive.
It really was an illusion of death, wasn't it? But it was all fundamentally happening in a 2D plane. Our source, Muse Hill, really nails this initial confusion. People wondered, was it pre-rendered, like just pictures, or was it actually tile-based? Because it seemed way too varied, too fluid, to just be simple squares laid out next to each other. Sometimes you'd even see textures looking a bit stretched on a hillside, which kind of hinted that something more dynamic was going on. It's that classic feeling, right? You see something cool in an old game, and you just have to know how they pulled it off under the hood.
Exactly. It felt like there had to be something more complex at play. So when the answer finally came out, confirmed both by Zane Dubia digging into the code and Raf Custer just saying it flat out, it was kind of a shock. The terrain was tile-based, which, for how complex it looked in 97, is pretty amazing. It completely flips that initial assumption that it had to be pre-rendered or some kind of proto-3D thing.
Yeah. It was astonishing, yeah. And not just, any tile-based world. We're talking about something on an absolutely epic scale. The original map, at least the version Zane Dubia was dissecting, was a mind-boggling 6,144 tiles wide by 4096 tiles high.
Ooh.
Yeah, think about that. That includes the main world, which was 4096 by 4096, already massive. Plus this extra strip, 2048 by 4096, for all the dungeons and the new world from the Second Age expansion.
Yeah.
It was basically a digital continent.
That scale is just hard to wrap your head around, especially for the late 90s. Think about the hardware back then. People were running this on, Pentium 166s with maybe 32 megs of RAM.
If you were lucky.
Right. So building a world that huge, that explorable, and making it feel dynamic, all with tiles, that was a massive challenge. It shaped everything, didn't it? How they made content, managed data, how we experienced the world. It really pushed that feeling of exploration, of living in this persistent place, not just jumping between small zones.
Yeah.
And you can immediately see why the tools they built became so critical. We'll definitely get into that.
Oh, absolutely. And for anyone thinking about large worlds in monogame today, even with modern hardware, managing assets and streaming for a tile map that big, it still presents real challenges.
Okay, so let's get into the real nuts and bolts. The anatomy of a UO terrain tile. This is where the magic really happens, and probably super valuable if you are trying to recreate this kind of system.
Right, so the core terrain data lived in this custom file, map0.mul. That MUL extension was pretty common back then, basically their own way of packing game data efficiently.
And the absolute key, the secret sauce maybe, how incredibly tight the data was. Each terrain tile only used 3 bytes of information.
3 bytes. It's astonishingly compact for a world that size. And those 3 bytes held 2 things. First, a 16-bit index. That just told the game what kind of tile was, visually grass, dirt, stone, water, whatever.
Okay, so 2 bytes for the tile type. What was the 3rd byte?
That was the critical one, an 8-bit altitude value. Now here's the really clever part, and maybe the most important detail to grasp, that 8-bit altitude. It only applied to the topmost, the northwest corner of that specific tile.
Only one corner?
Only the northwest corner. That single design choice dictated the whole elevation system. An 8-bit value gives you 256 height levels, which was plenty for variety. It did mean, maybe, that very smooth slopes over short distances could sometimes look a tiny bit like stairs if the height changed too fast between tiles. But usually, it worked incredibly well.
So if only the northwest corner's height is stored, how did the other three corners, northeast, southwest, southeast, get their height? Where did that data come from?
See, that's the other clever bit. Implicit propagation. Saved a ton of space. Their heights weren't stored separately at all. They were just derived from the neighboring tiles. Specifically, the northeast corner got its height from the northwest corner of the tile just to the east, at x plus 1 y.
Okay.
The southwest corner got its height from the northwest corner of the tile just to the south, at xy plus 1.
Yeah.
And the southeast corner, pulled from the northwest corner of the tile, diagonally southeast, at x plus 1, y plus 1.
Got it. So it's like a domino effect almost. Each tile sets its own top left height, and that ripples out to define the corners of its neighbor.
Exactly, like a puzzle fitting together. It creates this surprisingly continuous surface across the whole map, even though the data itself is really sparse. And a little detail for continuity, the map wrapped. Tiles at the bottom edge actually got some height data from tiles way up at the top. Kept it seamless.
So for someone building this in monogame, that propagation is key. You don't need a whole separate height map file. The altitude is baked right into the tiled data layout. Pretty elegant.
Very elegant. Okay, so we have the data structure. Now, how did they turn those 3 bytes into the terrain we actually saw? There were basically 2 main ways the game would draw a tile, and it depended on those altitude values.
2 methods.
Yeah. Method 1. If all 4 corner altitudes for a tile were the same meaning, it's perfectly flat ground. The game did the simple thing. It just drew a pre-rendered static isometric image, a raw tile. These were stored as 44 by 44 pixel graphics in another file, RTMUL, which held all the static art. This was super fast, just a basic blit operation copying pixels directly to the screen. No heavy lifting.
Makes sense for flat areas, but what about the slopes, the interesting bits? That's where the magic must have happened.
That's where it gets really interesting, yeah. Especially if you're thinking about coding this. If the 4 altitude values were not equal, meaning you had a slope or some height difference across the tile, then the game dynamically drew what they called a textured quad.
A quad, okay, so like a 4-sided shape.
Exactly. Though technically, any quad is rendered as 2 triangles. And Zane Dubia, from his observations of how the screen redrew, strongly suspected it was always split the same way into a left half and a right half. That specific triangulation matters if you're building the rendering pipeline.
Right, 2 triangles making up the sloped tile face.
Precisely. And these textured quads didn't use the small 44 by 44 art. They used bigger, more detailed textures, maybe 64 by 64, or even 128 by 128 pixels. Those lived in another file, textmaps.mul. And here it is. The absolute core mechanic, the cornerstone for recreating this effect. The corners of that quad were offset vertically on the screen based on their altitude.
But offset how?
By a specific amount. This was the famous 4-pixel rule. For every single unit of z height difference, plus 1 or minus 1 altitude, the game moved the corresponding corner of that quad up or down by 4 pixels on the screen.
Okay, so a corner with a higher altitude value would literally be drawn 4 pixels higher on the screen for each point of difference.
Exactly. That simple, consistent 4-pixel offset is how they created such a convincing illusion of height and slope using just 2D graphics.
That is incredibly clever, just shifting pixels based on a height value.
Yeah. For a monogame dev, this translates directly into your projection math. You take your standard isometric coordinates for the tile corners, and then you apply an additional z offset to the screen y-coordinate scaled by that 4-pixel factor. It's the fundamental rule that defines the whole world's perspective.
Brilliant. And so simple conceptually. But wait, drawing all those textured quads dynamically even with that rule. That must have been demanding for 1997 hardware, right? They couldn't have redrawn the whole screen every frame.
No way. Absolutely not. That would have crippled performance. Which leads us to the other crucial optimization. Dirty rectangles. A classic technique from that era.
Dirty rectangles, meaning they only redrew parts of the screen?
Exactly. The game didn't redraw everything all the time. When something changed, your character moved, an animation played, you dropped an item, the game figured out which rectangular areas of the screen were affected. It marked those areas as dirty.
Yeah.
And then it only redrew the pixels inside those dirty rectangles. Everything else stayed the same from the previous frame.
That makes so much sense. Conserves huge amounts of processing power and memory.
Absolutely essential back then. Remember the specs, Pentium 166, 32 megs of RAM? You had to say every cycle you could. Optimizing every draw was non-negotiable to get that lush world running smoothly.
It's a great lesson, really. Even for modern development in monogame, while machines are way faster, thinking about dirty rectangles or similar partial update strategies could still be useful, maybe for complex UI or huge 2D scenes. Resource management never goes out of style.
It really doesn't. Constraints breed invention, like you said. And speaking of invention, let's pull back the curtain a bit on the actual creation process. The synergy between the art and the engineering behind UO's terrain is fascinating. The very first attempt at making the terrain look 3D, this was way back in late '95, was actually Raf Coaster, just using an optical illusion.
An optical illusion?
He basically took the existing flat terrain tiles and created lighter and darker versions. Then he painstakingly placed them strategically to suggest different heights. You saw similar tricks in games like The First Legacy of Kain or lots of old JRPGs. Clever, but still fundamentally flat.
Okay, so it looked kind of 3D but wasn't really changing height.
Right. But then Rick Delishmet, one of the programmers, saw what Raph was doing. And according to Raph's account, Rick just said something like, I bet I could actually give you real 3D terrain.
Bold move.
Yeah. And that comment basically kicked off the development of the actual texture mapping system we just talked about, the textured quads, the Z offset. Yeah. Rick built the core engine for it.
And that crucial 4-pixel interval, the magic number, was that just Rick's idea?
No, that came out of intense collaboration. Raph and Rick worked super closely together, tweaking that value. They experimented. They had to worry about visual glitches, like things clipping through each other weirdly. And performance was always key. They had to make sure stuff rendering near the bottom edge of the screen behaved properly. It wasn't just code, it was tech art. Finding that perfect 4-pixel sweet spot that looked right and ran fast enough, lots of back and forth.
That makes sense. It had to look good and work technically. What about specific features, like those nice sloped embankments between terrain levels?
The embankments. Raph specifically mentioned that the decision to split the textured quads into that left half and right half we talked about, that was what he called a tech art solve, specifically for making those embankment textures work well.
A tech art solve, meaning the rendering method influenced the art creation.
Directly. And this is amazing. Raph Coaster himself created those textures. He literally took bits of dirt tiles, bits of grass tiles, mashed them together in Photoshop. And then, using the burn tool like a digital paintbrush, he hand-drew runnels on them. Those little grooves or channels you see, making it look like eroded earth or worn paths, he drew those by hand.
Wow. So the lead designer was also doing detailed texture art, directly tied to how the engine rendered slopes.
It really highlights how integrated things were back then. Designers often wore multiple hats. They needed deep understanding of both the art and the tech. They were literally handcrafting the world based on engine constraints. It's a kind of bespoke creation you don't see as much in today's huge specialized teams.
Yeah, that's a different world. For someone recreating this in monogame, it suggests you don't just code the renderer. You have to think about how the art fits that renderer, maybe even make textures in that same spirit.
Absolutely.
Yeah.
Okay, so the terrain is rendered. It looks great. Now, how do you put stuff on it? How did objects and players navigate this dynamic height-mapped world?
Right, placing items, buildings, characters. How did that work with varying Z heights?
Objects also had a Z value, their height, and they were sorted for drawing based on a very specific anchor point, the exact center of their bottom row of pixels. That point determined where the object sat vertically in the world.
Okay, an anchor point. And then how did the game decide what to draw in front of what? The layering must have been critical.
Oh, incredibly critical. The drawing order was super precise and essential for the illusion. It went like this. First, draw things back to front. Stuff further away gets drawn first.
Standard depth sorting.
Right. Then, for things at the same depth, draw left to right.
Okay.
And then crucially, within the same XY tile location, draw things from bottom Z to top Z. Lower objects first, then higher objects in the same tile space.
Back to front, left to right, then bottom Z to top Z within a tile. Got it. That hierarchy makes sense for preventing weird overlaps.
Exactly. And for a monogame dev, getting that sorting algorithm right is absolutely key for correct sprite layering. You'd need to sort your render list based on all those criteria every frame, or at least within your dirty rectangles. Otherwise, characters will walk on top of walls.
Yeah, visual chaos. Now, didn't this system lead to some interesting visual quirks, like with buildings?
It absolutely did. It led directly to the famous UO roof popping, classic UO phenomena.
Ah, yes, I remember
It
that.
was a direct result of trying to be efficient. Basically, if you were standing in a tile and there was something else in that same tile above roughly your character's head height, like a second floor or a roof, the game just wouldn't draw it at all.
So you walk into a house.
And poof, the ceiling and everything above it just vanishes instantly. It wasn't really a bug, it was a deliberate choice to save rendering overhead. Don't draw what the player theoretically can't see directly above them.
It was definitely noticeable. And I guess that meant artists had to be really consistent, right?
Totally. They had to establish a standard Z height for what counted as the next floor up and make all wall and building art adhere to that standard. It was a crucial art constraint driven by the rendering system.
What about really wide things like big statues or walls wider than one tile? Did they clip, strangely?
They could, yeah. If a sprite was wider than the standard 44 pixels, its edges could easily clip through other objects because of the strict tile-based drawing order. The solution was pretty pragmatic, though probably tedious at first. They just broke very wide sprites into multiple 44 pixel wide strips, placed them side by side. So a big dragon statue might actually be 3 separate sprites lined up.
Clever workaround.
Raph mentioned they later automated that slicing process in Metaplace, but yeah, early on, it was likely manual art prep.
They also had that really efficient wall system, didn't they? Richard Garriott was impressed by it.
That's right. They developed this very clever wall tile set. It was designed not only to minimize network traffic, which was huge for an MMO back then, but it also had this built-in benefit of naturally preventing players from getting stuck in weird corners where they'd be completely hidden from view. Solved a technical problem and a gameplay visibility problem in one go. Garriott was apparently quite impressed, yeah.
Okay, so objects are placed, drawing order is sorted. How did movement work? Walking up slopes, stairs, dealing with impassable areas.
Objects could have flags. 2 important ones were surface and stairs. The ground, the terrain itself, was basically a default surface. Players could stand on it. Your character's feet, that Z anchor point we mentioned, would automatically snap down to the first surface directly below it, kept you grounded.
And stair.
The stairs flag lets you walk between surfaces at different Z heights. It handled the transition smoothly, letting you go up and down slopes or actual stair objects.
What about places you couldn't go, like cliffs or deep water?
If the Z height gap between 2 adjacent surfaces was too big, like a cliff edge, the pathfinding system just marked it as impassable. Your character wouldn't be able to plot a route across it.
And how did it know it was impassable? Was there a separate map layer for pathfinding?
Here's another really elegant part. No, there wasn't a separate pre-calculated pathing map like you see in many modern games. That would have been enormous and complex to maintain. Instead, impassability was defined right on the tile art itself, within the object's definition. The game didn't pre-compute paths. It procedurally read the pathing information directly from the map tiles and object properties as needed.
Wow. Okay, so the pathfinding queried the actual world data on the fly.
Essentially, yes. It was a surprisingly lean and efficient solution. Simplified the data hugely. For monogame, it means your Pathfinder could potentially work directly off your tile map and object data, reducing redundancy and allowing dynamic map changes without recalculating a whole nav mesh.
That is seriously elegant. Now, the dungeons, the underground areas. UO gave this amazing feeling of going deep, deep underground. How did they pull that off on what we now know is basically a height map surface?
Ah, the great underground secret. It was mostly a brilliant illusion, a fantastic visual trick.
An illusion? How?
They had this special terrain tile.
Yeah.
It was solid black, but it had a graphic of a cave entrance drawn on it. Now, when your character walked onto the specific black tile, unlike normal terrain, it didn't snap your Z height down to a surface.
Yeah.
This allowed you to effectively walk off the regular terrain surface and sort of under it.
Yeah.
And as soon as you did, all the terrain tiles above your Z level would just stop rendering.
Whoa. So the world above you just vanished.
Exactly.
Yeah.
It instantly felt like you were descending into darkness, into the earth. The visual cue was powerful and immediate, sold the illusion perfectly.
But some dungeons felt huge, way bigger than could possibly fit just under the surface map.
Right, for the really big, sprawling dungeon complexes, classic game dev smoke and mirrors. Teleportation. You'd enter the cave mouth, maybe walk under for a bit, and then bam, you'd be silently teleported to a completely different, hidden area of the main world map. An area far away, usually filled with just solid black terrain tiles, where the actual dungeon layout was built.
So you weren't actually underground at all, just in a different blacked out part of the surface.
Pretty much. It created this perfect illusion of deep subterranean exploration, all without needing complex 3D spaces or digging holes in the main map data. Just clever design and misdirection.
That's fantastic. It really shows how creative thinking can overcome technical hurdles, which brings us neatly to the tools they use to actually build this massive world.
Yes, the tools became absolutely critical because, as they found out preparing the alpha map for E3 in '96, trying to handcraft every hill and valley on that scale is just too slow, unscalable. They were ending up with huge areas of boring, flat terrain simply because they couldn't manually detail everything fast enough.
So they needed automation badly.
Desperately.
Yeah.
And this led to the birth of a script, which Raf Koster lovingly describes as a terrible little scripting language.
Terrible.
Apparently, Rick Delishman whipped it up super quickly out of necessity. Raf said it had horrible syntax like variables needed, hashtag tag around them, statements used at IFR. And weirdly, it didn't load into memory. It ran commands directly off the disk file. Very raw.
Raw.
But incredibly powerful for its time. And here's a testament to Raf Koster's dedication. He learned this quirky, difficult language literally the night before the E3 alpha test opened.
Wow, talk about cramming.
Total crunch time.
Yeah.
But knowing his script immediately let him automate basic stuff. Things like querying a tile's ID or z-value, raising or lowering terrain automatically, placing objects like trees randomly on forest tiles, or adding subtle rumpling to flat areas to make them look more natural.
So even that rough tool was a huge leap forward from placing every single tree by hand.
Massive. For anyone building level editors or procedural tools in monogame today, it's a reminder. Even a simple scripting interface for automating repetitive tasks can be incredibly powerful, even if the syntax isn't beautiful. It just lets creators work faster.
And these tools didn't stay basic, right? They evolved.
They did. Later, Rick Delashman extended the API for Wombat, which was the game's main, more sophisticated scripting language, so that Wombat scripts could actually call and run the scripts. It integrated the systems.
Okay, so Wombat could control a script.
Exactly. And then Raf built on that. He created this big menu-driven front end using Wombat. Suddenly, those powerful but clunky scripts became accessible through a much friendlier interface. This unlocked really complex automated world building. They could write scripts to, say, select all the tiles in a big rectangle, apply a gentle slope across them, add random noise or roughening, then smooth it out a bit. And crucially, they could automate finding borders between terrain types like forest meeting grass and placing the correct, specific hand-drawn transition tile there.
Ah, the transition tiles. Because they didn't have smooth blending back then. You needed actual art pieces for where grass met dirt, for example.
Right. No automatic blending like modern engines have. You needed explicit art for every type of transition. Imagine placing all of those manually across that enormous map. The tools automated finding the spots and putting the right transition piece down. It saved unbelievable amounts of time.
That automation must have been revolutionary for them.
It absolutely was. And here's the truly mind-blowing part. Raf mentioned that, as far as he knows, this very tool system, Wombat calling a scripts, with that menu front end, is reportedly still being used by the current UO team today.
You're kidding. Over 20 years later.
That's what the source says. It just shows that if you build a powerful, effective tool, even if it's a bit rough around the edges, it can have incredible staying power if it solves a fundamental problem well.
That's incredible. A real testament to its utility. Invest in your tools, folks. Even the terrible ones might outlive everything else.
It's a great lesson. And understanding these tools helps explain some of the, let's say, variations in quality in the UO world itself. There were successes, but also some missed opportunities, especially early on.
Like the mountains in the original release.
Exactly. The original mountain biome is often seen as, well, a bit poor design-wise. The designer working on them, apparently before their really powerful automation tools were fully developed or maybe understood, ended up just painting huge swaths of mountain areas as completely impassable. Instead of getting those cool wedding cake tiers, navigable plateaus at different heights, they just got these big dead flat zones you couldn't even walk on.
Flat, impassable mountains. That sounds odd.
It was. And Raf estimated this approach effectively wasted almost a third of the game's potential continental landmass. Just huge areas locked off because of how the mountains were initially designed and implemented.
Wow, a third of the map basically unusable. That's huge.
Massive. Raf apparently tried a last-minute fix, creating much darker versions of the mountain rock tiles and scattering them randomly just to add some visual contrast and break up the flatness. Trying to salvage the look, at least.
Making the best of a bad situation. But then things improved significantly later, right?
Oh, hugely. Compare that to the Second Age expansion map, T2A. That map was a triumph. largely because it fully leveraged the new automation tools. The difference was night and day.
That's the one with the really noticeable wedding cake layers, right?
That's the one. The process was totally different. They'd start by painting the whole map flat with placeholder dummy tiles. Then they'd run automated wombat scripts. Scripts would go through raising entire tiers of elevation, randomizing the tile types within those tiers so it didn't look repetitive, applying smoothing algorithms, adding gentle slopes, and automatically handling all those crucial transition tiles between different heights and types.
So most of the big elevation changes and texturing were done by the tools.
The vast majority. According to Raf, only the really tricky bits, tight ramps between levels, specific narrow passages needed careful hand editing afterwards. This automated layered approach is why the wedding cake structure felt so clear and deliberate to players.
It really shows what a difference the right tools make, going from accidentally losing a third of your map to being able to sculpt these complex tiered landscapes automatically.
It's a perfect illustration. For monogame world building, it drives home that point. Automate the broad strokes, automate the repetition, so you can spend your precious time on the unique, handcrafted details that really matter.
Makes perfect sense. Okay, let's touch on a few other visual details before we wrap up. What about the art assets themselves? Was everything pixel art? Was anything 3D?
Good question. There's often confusion there. Raft clarified. All the terrain tiles and static world objects, like furniture or buildings. Meticulously hand-drawn pixel art. He even mentioned drawing a lot of them himself.
Okay, so the world itself was hand-drawn. What about characters and monsters?
Those were different. Creatures, player characters, armor, weapons. That stuff was done as 3D models first. Then they were rendered out from multiple angles on turntables to generate all the 2D sprite frames needed for the isometric view and animations. Doing that by hand would have been truly impossible.
Right, that makes sense. Rendered 3D models for animated things, hand-drawn pixels for static things.
Now, there's an interesting bit of speculation about whether artists did extra work on those renders. The question came up, did they do manual cleanup or add pixel arty touches to the rendered creature sprites, especially for the original game and T2A?
Like hand editing the renders. Why?
The theory is that maybe this super time-consuming pixel polishing step is why the visual detail or style seemed to shift a bit in later expansions. Perhaps they couldn't maintain that level of manual touch-up with bigger teams or faster schedules. It's not confirmed, but it speaks to the potential level of craft involved early on.
Interesting thought. What about that distinction between terrain tiles and object tiles you mentioned earlier, like for wood flooring?
Right. So if you had wood on the ground, part of the main landmass, it was a wood terrain tile, rendered efficiently as part of the base terrain mesh. But if you needed wood floating midair, like a dock over water, you couldn't use a terrain tile. You used a separate wood flooring object tile. This was drawn like any other object, as a sprite layered on top of the water terrain below it.
So walking from the shore onto a dock looked seamless to me, the player.
Looked totally seamless, yeah. But under the hood, the game switched from rendering one efficient terrain draw call to potentially two or more, one for the water tile underneath, one for the wood floor object tile on top.
That's a subtle but important distinction for optimization.
Definitely. For monogame, it highlights thinking about when to use efficient tile maps versus layered sprites, even if the assets look identical. Different rendering paths for different contexts.
How about effects like lighting? Dungeons had that cool colored lighting.
Surprisingly simple. Colored lighting was mostly just a tinted, semi-transparent overlay mask drawn over the scene. No complex per-pixel lighting calculations or anything like that.
Wow, really? Just a color filter?
Pretty much. And the general terrain shading, that soft look, primarily standard Garode shading, calculates color at the corners of the polygon, smoothly blends it across the face. Very efficient for the time, gave it that characteristic smooth but not too sharp look.
Okay, one last fun one. The water tiles. Some water actually moved, right?
Right.
Didn't players find a way to mess with them?
Oh yeah, some water tiles were animated, dynamic. And yes, the famous water tile bug. Apparently, these dynamic water tiles weren't properly flagged as non-movable world features. They were treated like regular items.
Oh, players could pick them up.
They could. Players figured out they could literally take water tiles out of rivers and oceans, leaving holes in the world. And even better, they could carry them around. Portable water sources.
No way!
Yes, leading to the legendary stories of players fishing out of the backpacks because they could just drop a water tile anywhere and cast a line. A perfect example of emergent gameplay hitting a system oversight. Hilarious.
That's amazing. Player ingenuity, or bug exploitation at its finest. What a journey this has been, really peeling back the layers of UO's map tech. It's incredible, really. This clever tile-based system fooling us all with its depth. That specific 4-pixel offset trick-making slopes appear, the art and engineering working so closely together.
And those tools, a script and wombat, born from limitations but enabling so much. These old-school methods just hammer home lessons about efficiency, smart problem-solving, and how powerful a good toolset can be, even decades later. They built that world because of the constraints, not just despite them.
It really makes you think, doesn't it? UO's map, technically simple by today's standards, 2D ISO, pixel offsets, no fancy shaders, yet it felt so vast, so complex, so real in a way. What can developers today, with all our amazing engines and power, learn from how that UO team worked within their tight box? How do we build worlds that feel that immersive, that believable?
Yeah, it's a great question to ponder. Does all our modern sophistication sometimes obscure those core principles? Clever design, elegant data, smart tech art solutions, the things that made UO work so well, are we always using our massive resources to create that fundamental depth and engaging experience? Or just layering on polish? Maybe the big lesson isn't just what tech you have, but how creatively and frankly intelligently you apply it. UO was pure ingenuity.
A really powerful thought to leave things on. Thanks for joining us on this deep dive. We'll see you next time.